Welcome back to our channel. In today's tutorial, we're diving deep into a critical topic for any Java developer: debugging multi-threaded applications. Multithreading can significantly improve application performance, but it also introduces complexity and potential bugs that can be challenging to catch. So, let's arm ourselves with the knowledge and tools to debug these issues effectively. First, let's understand what multithreading is. Multithreading allows concurrent execution of two or more threads. It's useful for tasks that are independent and can be executed simultaneously, improving the performance of CPU-intensive operations. However, alongside its benefits, it introduces challenges like race conditions, deadlocks, and thread starvation. For our demonstration, we'll create a simple multi-threaded Java application that performs some calculations and simulates both a race condition and a deadlock. We'll use this application to illustrate various debugging techniques. Let's get started by setting up our multi-threaded environment. We'll begin by creating a simple Java application. Open your IDE and create a new Java project. Let's start with our main class. Now, let's create two threads that will access a shared resource. We'll create a counter that both threads will increment, which will allow us to demonstrate a race condition. Here's the code for the two threads. Now, we'll modify our main method to start these threads and wait for them to finish. This will allow us to see the race condition in action. Run the application now, and you will notice that the final count is often less than 20,000. This is because of a race condition. Both threads are trying to increment the same variable simultaneously. With enough runs, you'll find that due to thread scheduling and timing, increments can be lost. To debug this issue, we can utilize techniques such as adding print statements or using a debugging tool provided by our IDE. Let's start with print statements to understand the order of execution. With print statements in place, when you run the application again, you should see the thread names indicating how they are incrementing the counter. You might notice that both threads are incrementing the count at the same time, which leads us back to our race condition issue. To address this, we can use synchronization in Java to ensure that only one thread can access the increment method at a time. Let's modify our counter class to include the keyword synchronized. Now that we've made the increment method synchronized, let's run our application again. You'll notice this time the final count should be consistently 20,000, as we have eliminated the race condition. Next, let's explore deadlocks. A deadlock occurs when two or more threads are blocked forever, each waiting on the other to release a resource. To illustrate this, let's create two threads that will attempt to acquire two locks. In this example, if two threads attempt to lock 1 and lock 2 simultaneously, they may enter a deadlock situation, where each thread is waiting indefinitely for the other to release the locks. Let's modify the main method to demonstrate the deadlock. We will create two instances of the lock class and start two deadlock threads that will operate on these locks. When you run this application, you may notice that it never completes. This is because the two threads are deadlocked. Let's add a timeout to our lock method to illustrate how one could detect such a deadlock scenario. This simplistic try-lock method can be further developed to return a result based on whether it acquires the lock successfully or not. It's important to note that detecting deadlocks typically requires more sophisticated mechanisms or frameworks. In addition to coding practices, Java provides various tools and frameworks like Java Visual VM and JConsole that can help monitor threads in real time and detect potential deadlocks. These tools give you a graphical view of thread states and resource monitorings, like CPU and memory usage. As a next step, let's wrap up our session with tips on debugging multi-threaded applications. Here are some strategies to keep in mind. First, always strive for thread safety by utilizing synchronized blocks or classes wherever shared resources are accessed. Second, employ logging to understand the flow of execution and identify where threads are waiting or being blocked. Lastly, utilize modern concurrency tools such as executors, locks, and the java.util.concurrent package when developing complex multi-threaded applications. That concludes our tutorial on debugging multi-threaded applications in Java. Remember, always practice thread safety and leverage tools available to you for monitoring and diagnosing issues. Thank you for watching, and if you found this video helpful, please like and subscribe to our channel for more Java programming tutorials. Until next time, keep coding.